let's introduce P series. So P series is defined as 1 over k to the p, the summation k from 1 to infinity. So for instance, when p is 1, then you get the harmonic series 1 plus 1 over 2 plus 1 over 3 and so on and so forth. When p is equal to 2, then you get 1 plus 1 over 2 square plus 1 over 3 square and so on and so forth. Okay. Now this table here gives us the partial sum for the harmonic series for different n. And as we can see, when n is getting bigger and bigger, the partial sum is getting bigger and bigger. Of course, it doesn't increase too fast, right? It increases so slow. However, it doesn't. It certainly we observe that it's getting bigger and bigger. So I would say it diverges. The next test we want to study is the integral test. A comment I have is try not to use this if the function is too complicated. We are going to study a whole bunch of different tests, so you have a lot of options. And this integral test says if f is continuous, positive, and decreasing. So it gotta be decreasing, okay? And I actually have another comments down below. It doesn't have to be always decreasing. It just needs to be ultimately decreasing. For instance, well here the graph we have shows decreasing, but as long as it's ultimately decreasing, for instance, you can have some increasing, and then at some point from that point on it must be always decreasing. So it's okay to have some increasing but ultimately decreasing. And let AK be f of k for k from 1 to 3 and so on and so forth. That means A1 is F1, A2 is F2. So if you have a series 1 over n, then that means your f of x is 1 over x. That's what it means. Okay. This theorem says these two, the series and this integral, they converge or diverge at the same time. They either both converge or they either both diverge. Okay, we went through the common number 1. Common number 2, the index k could start with any number, not necessarily 1. That means, hey, this doesn't have to be 1. You can start with 10 or 100 or 800 and so on and so forth. It doesn't really matter. This k can start with any number. In general, do not expect this series and this integral to be equal. They're not equal. Now, how do we let's try to understand this theorem, why this theorem is true. So take a look at the graph given here. So the left this graph, so it's when n is 1, we use this is f of x, so we actually use f of 2 to construct this integral. To construct this rectangle, and this is f of 3 and so on and so forth. So this is a2, a3, a4 and so on and so forth. Okay, and we can see that this sum is less than or equal to this integral. Obviously, this is obviously because there are so many extra little this area not covered by those rectangles, right? So this area under the f excuse me, so the area under f is certainly greater than the area of those rectangles. Similarly, now when we construct rectangles using the left endpoint of each interval, of course these rectangles have more area than the area below this function, so therefore this is also true. Now let's discuss. If this guy diverges when this n is approaching infinity, in that case this is infinity, right? So like I said, this k doesn't have to to start with 1. It can start with any number. But when this diverges, this guy is bigger, so it must be diverge. It must diverge. So when this diverges, the integral must diverge. Okay, so that's the first inequality. Let's look at the second inequality. When this guy converge, okay, when this guy converge, then this is even smaller. Therefore, it must be it also must converge. So that's why we say we can see that they either both converge or both diverge. Now, another way to look at that, just give you a little more explanation. So if this guy converge, the integral converge, and this is smaller, right? This is smaller, so therefore this guy also converge. When the integral diverge, and this guy is even bigger than the integral, therefore this guy will diverge. So this is another way to look at that. They both diverge and converge at the same time. Okay, so this is the integral test. Now let's take a look at its application here. The first application is this guy, right? Let's first try the divergence test. The divergence test says, hey, this is approaching 0. This term is approaching 0, and when k is approaching infinity, a divergence test is inconclusive. So it doesn't help at all. So now let's try the integral test. Okay, so let's try the integral test. So to determine whether it diverges or converges, let's find the integral of this function, k squared plus 1 dk in this case. If you're not comfortable with k, you can just rewrite it as x, if you like, x squared plus 1 dx. Now we go back to chapter 7, right? You need to identify a method. It looks to us we use substitution called u as x squared plus 1, and du will be 2x dx. And when x is 1, your u is 2. When x is infinity, your u is x squared plus infinity squared plus 1, of course, infinity. So with that, your integral becomes 2 to infinity. And x dx will be replaced with 1/2 of the du. And x squared plus 1 will be replaced with u. So at the end, this is 1/2 natural log of u, evaluate from 2 to infinity. So when you plug infinity, it's already infinity. So therefore, you know this is infinity because it diverges. Therefore, we can conclude this series diverges. Okay. This is the first example. I would like you to try the second example. It's all about evaluating this integral 1 over x natural log of x. Okay, so determine a good method to integrate this integral. Now we are gonna look at one result for the p series. So when p is 1, the harmonic series is divergent. So this is a famous result. Okay, because how do you determine that? You basically just evaluate 1 over x, 1 to infinity dx, and from the last chapter, we know that this is famous. This is infinity. This diverges. Therefore, this harmonic series also diverges. When p is greater than excuse me, when p is greater than 0 but not equal to 1, it will converge when p is greater than 1 and diverge when p is less than 1. And we talked about this result previously. So when 1 to infinity, 1 over x to the p dx, p greater than 1, then it converge, right? So this is consistent. This is very important. I want you to be very familiar with that. And when p is less than 0, this guy will diverge because the divergence test. So this is the well-known result that everyone should be familiar with.